Our next section in testing of hypothesis is large sample test. A sample is considered to be large in size if the number of units in the sample is more than 30. Otherwise, the sample is treated as small in size. So first our discussion is on large sample test, and here in the introduction of testing of hypothesis, we had discussed various terms related to testing of hypothesis like level of significance, power of test, critical region, acceptance region, then test statistic, etc. Level of significance is dealing with a probability. It's a probability of rejecting a null hypothesis when it is true. So to find this probability, we should know the length of the test statistic, the range of the test statistic where we reject the hypothesis. Test statistic is the statistic used for testing of hypothesis. And this test statistic will have a range of variation. The segment of the range of variation within which we reject the hypothesis is to be considered here as in the finding of probability for rejecting at zero. That means when we take the worksheet of, we can see that if the test statistic is say x bar, sample mean, and its range of variation is minus infinity to plus infinity and 0 in the middle, and if we treat these two limits a and b as the rejection region, critical region, its complement will be acceptance region. This will be AR, and here the other side of AR is from B to infinity. So this is that critical region that is between A and B. Now, level of significance is taken as probability of rejecting at zero when at zero true, which means that the probability of the statistic value x bar lies between it is the probability of x bar lies between A and B when H0 is true. So it's simply a computation of a probability. This is when H0 is true, and that is the level of significance, that is probability of rejecting H0 when H0 true. Likewise, we have the power of test as the probability of rejecting H0 when H1 is true. So when H0 true, that is the equation of the density function or the statistic distribution will be in the status H0 true, and in power of test we have taken H1 is true, therefore the test statistic distribution will be the status of H1 is true. Anyway, here this is merely a computation of probability of x bar between A and B. Therefore, the basic information for finding probability of any random variable within any range is its density function. For example, if you are given that x is a random variable with values some 0, 1, 2, etc. 10, and the probabilities are like 0.05, 0.15, 0.25, then some P 0.03, 0.08, etc. It goes like that. So here this is the probability of 0, this is the probability of 1, 2, 3, 4, etc. What is the probability of x lies between 1 and 3? What is the probability of x between 1 and 3? You can see that probability of x between 1 and 3, you can refer to this table 1.15, 2.0, 0.25, 3, 0.3. So probability of x between 1 and 3 will be sum of these two. But to find this probability, the essential information is the probabilities at the points 1, 2, 3, etc. Suppose this information is not given to us, we cannot find this probability. Therefore, the essential information to find the probability of a random variable within any range is its density function. Likewise, if x is a continuous random variable, say x has a range of variation between -3 and +3, and suppose its density function small f of x is equal to 1 by 6. What is the probability of x between 1 and 2? So we can do that by integrating 1 to 2 1 by 6 dx. We integrate here because the variable is continuous. We say x lies between -3 and +3. So since the variable is continuous, probability of x between 1 and 2 is integral 1 to 2 1 by 6 dx. 1 by 6 is the density function of x when x lies between -3 and 3. Thus, the essential information to find the probability of any random variable within any range is the information about the distribution of the statistic. Therefore, without knowing the distribution of the statistic, we cannot find the probability of any interval. Therefore, in order to set the significance level so that probability of rejecting at 0 when at 0 is true minimized, we should know the density function of the test statistic. So if you know the test statistics distribution, based upon that distribution we can fix the rejection region satisfying the prefixed value of significance level. So we will be given a freedom, say 5% or 1% to reject a true hypothesis. That is the value of significance level. Based upon this value of significance level, we can identify a segment of the test statistic such that it's the probability of rejecting at 0 when at 0 true is that 5% or 1%. But the information required for setting the critical region or rejection region satisfying the prefixed value of significance level, this density function of the test statistic. But we find that the statistics which possess standard distributions are very rare. So in this situation we have the importance of central limit theorem. So in central limit theorem we find that when the samples are sufficiently large, irrespective of the distribution of the population distribution may be exponential, may be Poisson or uniform or anything. When the sample sizes are large, most of the statistics can be considered as normally distributed. That's a very important milestone in the history of probability theory, and therefore the central limit theorem is supposed to be the most important theorem among the various theorems of probability theory, because it gives a wide opening for various statistics which don't have distributions. So whenever the sample sizes are large, you can take any form of statistic, any equation of statistic. When the sample sizes are large, we can say that statistic follows normal distribution, and therefore these x1, x2, etc. xn constitute a set of independently and identically distributed random variables which have mean, mu, and variance sigma square. Then their sum Sn, that is the variable or statistic proposed, the sum Sn has normal distribution when n tends to infinity. And making use of this property, we here formulate the various test statistic considered in large sample test. That's the importance of central limit theorem in statistical inference. So we have x1, x2, etc. xn a set of identical random variables. Sn follows normal distribution with mean and mu and standard deviation root and sigma, or Sn and x bar are closely related because x bar is 1 by n Sn. The sigma is equal to 1 to n xi is taken as Sn. So x bar is sum of observations divided by number of observations. So using central limit theorem, we have the distribution of x bar also. That is, x bar follows n mu sigma by root n. So this x bar follows n mu sigma by root n is a statistic considered in test based upon test for mean or proportion in large sample test. So that's about the introduction of large sample test. In this case, we will consider four type of test procedures. two regarding mean of the population and the remaining two regarding the proportion of the population. So our first test is for mean of a population has a specified value, and this is considered when sigma known. By saying sigma known, we mean that the parameter, second parameter, that is population standard deviation, is known to us. That may be known from the past experience of the investigator, etc. And that is the condition is imposed because the statistic will be meaningful only when the sigma is value of sigma is known to us. Therefore, the statistic x bar is considered for testing mean of a population has a specified value, and we have x bar follows n mu sigma by root n according to the central limit theorem. So using central limit theorem, we have this relation, and again we can standardize this x bar to transform this x bar to standard normal using this relation t equals x bar minus mu divided by sigma by root n, or this root n by sigma, that is by subtracting mean and dividing by standard deviation. Therefore this t follows n01. Therefore, the statistic for testing mean has a specified value is x bar minus mu 0 in root n by sigma. In every test procedure, there are four important steps. The first step is setting the null hypothesis, that is h0 mu equals mu 0 versus its alternative hypothesis. So in null hypothesis, there must be a fixed value for the parameter, and the alternative hypothesis is fixed according as the required test. For example, if the test is mean of a population is greater than mu 0, we will set h0 mu equals mu 0 versus h1 mu greater than mu 0, which is a right-sided test. Likewise, if the test is mean has a value of mean is less than mu 0, there also we set mu equal to mu 0 in null hypothesis, but in alternative hypothesis it will be h1 mu less than mu 0. It is a left-sided test. And the third case is two-sided test. The two-sided test is considered when mean of a population is equal to mu 0. Test is whether mean of a population is equal to mu 0. In that situation, we will set h0 mu equals mu 0 versus h1 mu not equal to mu 0, which is a two-sided test. We will consider the three different types of test constructions for the three different types of alternative hypothesis. So the first case is h0 mu equal to mu 0, and here then test statistic is x bar minus mu 0 root n by sigma. So the second step is identifying an appropriate test statistic. So the test statistic is taken as here x bar minus mu 0 root n by sigma. The third step is construction of various critical regions corresponding to various alternative hypotheses. So for the time being, we first take h0 mu equals mu 0 and versus h1 mu greater than mu 0, which is a right-sided test. So this test is said to be right side because in the alternative hypothesis, the values of mu greater than mu 0 are considered. Here the values of mu greater than mu 0 will appear in the right side of mu 0. That's why we say the test as right-sided test. Now, in a right-sided test, the critical region is T greater than T alpha, where T alpha is obtained from tables of standard normal distribution according to the value of significance level. That we can make clear from the graph given. Suppose alpha is the value of significance level. That is, significance level represents the probability for rejecting H0 when H0 is true. That is, it is the freedom offered for rejecting a true hypothesis. So it may be normally 5% or 1%. So we can note that the value of t will be 0 when x bar and mu 0 coincide each other. What is meant by x bar and mu 0 coincide each other? That is, sample mean is equal to the suspecting value of population mean, which means that the sample has perfect agreement with the proposed value for population mean. There is strong evidence to accept population mean as mu 0 itself. There is no question of, because sample full agreement to say population mean mu 0. So the situation x bar equal to mu 0, no question of rejecting the null hypothesis. But based upon the sampling scheme, there may be some level to which we can accept mu 0 itself. That level is to be fixed according to the freedom offered for rejecting a true hypothesis. Means this is the position of perfect coincidence between sample mean and population mean. We are ready to accept this sample mean as population mean. Now, proposed value of population mean again when it comes up to T alpha. So this is the position of T alpha. That is, the shaded sector is considered as the rejection region. This sector, shaded sector, has an area alpha. So 0 is the point at which x bar and mu 0 coincide. This T alpha is exactly here. I mean, I shall record T alpha a little bit towards left. That is not exactly the position it is displayed now. It is not here exactly. This is to be shifted, that position where it starts the shading. So this is the position of T alpha. Okay, so from T alpha to infinity, we reject the hypothesis. That is here given in the critical region. T greater than T alpha, reject at 0. So T is the axis here given with values. So this is T equal to 0. This is T equal to T alpha. So we have the margin to accept h0 mu equal to mu 0 between 0 and T alpha also. For example, if we are to test whether population mean as mu 0 equal to 100. If sample mean x bar also 100, there is no question of rejecting population mean as 100. But we are ready to accept sample mean some 102. Okay, suppose sample showed a mean 102. Now, if this 102 generates a value of t between this 0 and T alpha, that hike of 2 will be ignored. We will take mu 0 as 100 itself. The hike 100 to 102, 2 is insignificant. That hike 2 is insignificant, and that's why we consider this mu 0 100 is true. So that point where it becomes insignificant, that is considered as T alpha. If it goes beyond T alpha, we will reject the null hypothesis and accept the alternative hypothesis. So there is one T alpha corresponding to 102, and that T alpha 1 corresponding 102 is computed using the equation T equals x bar minus mu 0 root n by sigma. So we will substitute 102 here, 100 here, sample size, the known value of sigma here. Using that we can generate a value of T, and if that value of T lies in the margin that is between 0 and T alpha, we will accept. If it goes beyond T alpha, we will reject the hypothesis. Thus, in right-sided test, critical region is T greater than T alpha. We are making use of the freedom offered for rejecting a true hypothesis as alpha, that is 5% freedom, and that 5%, according to that 5% freedom, we set T alpha. Now you can set if 5% is the level of significance, then 0 to T alpha the area will be 0.45. That is T alpha to infinity it is 0.05. Therefore 0 to T alpha the area will be 0.45. So from the tables of standard normal distribution we can obtain the value of Z, or in the present case T, where the area 0.45 is obtained. You can see that this is the location of 0.45, and corresponding to this 0.45 in the margin we have the values like 1.64 and 65, which is exactly 1.645. So when the freedom offered to reject a true hypothesis is 5%, T alpha will be 1.645. And if it is 1%, again you can see that in the table 0.49 is the area, and it is clear that it is at 2.33. Therefore this T greater than T alpha is like T greater than 1.645 in 5%, and t greater than t alpha will be t greater than 2.33 when t alpha is 1%. Now this is the case of a right-sided test. In the left-sided test, the steps are very identical. We simply shift the sector of rejection, critical region, to the left side, and we say that the critical region will be t less than minus t alpha. Here also we are ready to accept till this t alpha lies between, you can see the next graph, t alpha lies between minus t alpha and t lies between minus t alpha and 0. If it goes below minus t alpha, then the null hypothesis has to be rejected, and that's why at 0 mu equal to mu 0 rejected when t is less than minus t alpha. Again, in two-sided test, we simply divide the total significance level value alpha into two equal parts, alpha by 2 in the left side and alpha by 2 in the right side. So minus t alpha by 2 or lesser, t alpha by 2 or greater are the two sectors of critical region. So we'll accept if it be between minus t alpha by 2 and plus t alpha by 2. We accept null hypothesis when the value of t calculated using the above equation, that is t equals x bar minus mu 0 root n by sigma, lies between minus t alpha by 2 and plus t alpha by 2, and reject if it is either less than minus t alpha by 2 or greater than t alpha by 2. Here the logic is the total significance level alpha has been divided into two equal parts. In the left side, minus t alpha by 2 or lesser is the critical region, and its size is alpha by 2, and the right side also same size, and the critical region is t alpha by 2 to infinity, so that the total area or total freedom given for rejecting a true hypothesis will be alpha by 2 plus alpha by 2 alpha. Thus we set the critical region according to the given value, the fixed value of significance level. Here for different significance level we have the values like alpha 0.05, t alpha 1.645, and t alpha by 2 will be 1.96, alpha 0.01, t alpha will be 2.33, and t alpha by 2 will be 2.58. Here one more assumption is made in this test statistics expression. Here we have sigma. Sigma is a parameter or a constant related to the population. So this statistic can be considered only when the value of sigma is known. So what we do when sigma value, say the sigma is a parameter value, so its value may not be given to us. If its value is given, we can put here. Otherwise, we can write s in the place of sigma, and that replacing sigma by s is true only when this sample is sufficiently large. So here first check goes to population standard deviation known or unknown. If it is known, we can make use of the given value of sigma. Otherwise, we have to put s in the place of sigma and proceed with same statistic equation, x bar minus mu 0 root n by s, and proceed with same steps of setting different critical regions for different alternative hypothesis. That's about the test for mean has a specified value. Likewise, the test for equality of two population means, here the only difference is in the null hypothesis and the test statistic. The construction of various critical regions will be identical to the first case because here also the statistic follows same distribution n01. A different construction of critical region is required when the statistics distribution is getting changed. So, but in large sample test, all the test procedures are with the support of central limit theorem, and according to the support of central limit theorem, all statistics will follow normal distribution. So therefore, in large sample test, no fresh construction of critical region is required for the different test procedures considered. So here the test is regarding equality of means of two populations. So we take H0, mu1 equals mu2, where mu1 and mu2 are the means of the two populations, and for that we consider two samples x1 bar and x2 bar from these two populations, and we are test whether x1 mu1 equal to mu2, and the statistic is x1 bar minus x2 bar divided by root of sigma 1 square by n1 plus sigma 2 square by n2. It follows n01. So we can calculate t using this equation, and the different alternative hypotheses are mu1 greater than mu2 right sided, and here the critical region will be as before t greater than t alpha, and the left sided test will be mu1 less than mu2, and here the critical region will be t less than minus t alpha, and the two sided test the critical region will be either t less than or equal to minus t alpha by 2 or t greater than or equal to t alpha by 2, which can be combined together like modulus t greater than or equal to t alpha by 2. This will include the both tails, that is t less than or equal to minus t alpha by 2 and t greater than or equal to t alpha by 2, the both tails, and therefore in two-sided test the critical region is modulus t greater than or equal to t alpha by 2. Now as before, if sigma 1 square, sigma 2 square are unknown, they are replaced by the sample variances, that is S1 square and S2 square, and this replacing is true here since the samples are large in size. The next is regarding test concerning proportions of a population. So here we have the null hypothesis H0 p equal to P0, that is proportion of a population has a specified value P0. Now the statistic is T equals P star minus P0 divided by root of P0 into 1 minus P0 by n. And what is P star? P star is a sample proportion. So if a sample of size n is taken from the population, and x is the number of units possessing that characteristic, the sample proportion will be P star, which is x by n, and T is equal to P star minus P0 divided by root of P0 into 1 minus P0 by n is used for testing proportion has a specified value, and this statistic also follows same distribution, normal distribution according to central limit theorem. Therefore there is no change in the construction of critical regions for various alternative hypotheses. So the various alternative hypotheses are the proposed value P0 above, that is P greater than P0, that is right sided test. The alternative hypothesis will be P less than P0 left sided test, and finally the third alternative hypothesis P not equal to P0. So the next test is regarding equality of proportions of two populations. So here we have H0 P1 equals P2. Here we have two different samples of sizes n1 from and n2. n1 the sample size of that drawn from population 1. n2 is a sample of is the size of the sample drawn from the second population. So this is p1 dash. P1 here is a dash. P1 dash is x1 by n1, and this is p2 dash, that is x2 by n2. That is proportion of the first sample and proportion of the second sample, and the statistic is p1 dash minus p2 dash minus p1 minus p2 by root of p1 q1 by n1 plus p2 q2 by n2, where p1 q1 and p2 q2 are the uh, values of the proportions of first population and second population, and this p1 p2 are given, they are given as equal only, but their equal value not given. So its equal value is estimated using this equation p star. P star is equal to n1 p1 dash plus n2 p2 dash divided by n1 plus n2. Therefore the final equation of the statistic will be p1 star p1 dash minus p2 dash divided by root of p star q star into 1 by n1 plus 1 by n2, where p1 dash is x1 by n1, p2 dash is x2 by n2, p star is n1 p1 dash plus n2 p2 dash by n1 plus n2, q star is 1 minus p star. So compute all these values of values involved in the equation, substitute and get the value of t. Again the critical regions are exactly same to that of the cases considered earlier, because here also the statistic has same distribution, that is normal distribution. So in all the tests considered in large sample, here the test statistic follow normal distribution. Therefore only one construction of critical region considered along with mean as a specified value is applicable for all the cases of the test in the title large sample test. Next, we will come to the various questions related to the large sample test.